All right, folks, we're going to talk about section 2-5, which is on implicit differentiation. It's for the week of October the 5th, and you can read the objective on here. Okay. Due to time, I went ahead and completed the warm-up for you using chain rule, but I'll talk about it real quick. Okay. First of all, remember, you differentiate everything on the outside, so 4 times the derivative of this. So it's going to be 4 times 3 because the exponent of 3 goes in front, subtract 1, you get the 2, and then that stays the same, and then multiply that times the derivative of that. You can also use the u substitution, will work as well. But when you end up with 12 times x to the third plus x plus 1, all times 3x squared plus 1. Because when you derive this, it's going to be 3x squared plus 1. All right, now same thing with sine of 3x. So derivative of sine is cosine 3x times the derivative of 3x, which is just simply the 3. All right, now g of x is a little bit more complicated just because it's got a couple different parts, but bring the 1/3 since it's a constant, leave it on the outside. And then we differentiate x, which is just 1, times this as it is, which is x squared plus 1. That's product rule and chain rule at the same time. All right, and then plus, when we derive this, the x, because we derived it in the first one, stays the same, so x times. Now remember, this is x squared plus 5 to the 1/2, so that 1/2 goes in front, and then you subtract the 1, so you get x squared plus 5 to the 1/2, and then you derive what's inside here, which is 2x, so that's how we get 2x. And then I just went ahead and combined them all together. Technically, you could be done at this point, but I just wanted to show you another step for it. So, and then that could be taken even further if you wanted to simplify it further. So there you go. All right. Now, implicit differentiation. You've been dealing with explicit differentiation where you get everything on y by itself. So you have y prime or dy dx. Now, implicit, right here, you have the following. You have the x's and the y's sometimes combined together all on one side of the equation. So we need to be able to find the derivatives dy dx of the equations that are both explicit and implicit. Now, with the explicit form, you could just do y prime or dy dx equals. Very simple. This one, not as simple, not as cut and dry, but that's what we're going to talk about here today. So to do this, we're going to determine what that really means. So dy dx, we must understand what dy dx truly means. All right. Indicates we're taking the derivative of y with respect to x. Now, we've used y prime, but what does it actually mean? It means the derivative of y in terms of x. So that's what dy over dx actually means. So, and I'm going to highlight that here in just a second. And this hasn't cause confusion because we have only taken the derivatives of the expressions involving x. So as of this section, we're going to expand it to include other variables, as you see. All right, now let's look at the following. The derivative in terms of x to the third. All right, so here's how it works. The derivative of x, of x to the third in terms of x is as follows. As you know, the 3 goes out front. It's just 3x squared times the derivative of x in terms of x. Let me state that again. 3x squared times the derivative of x in terms of x, because that's what that means. Well, this right here is just 1, so it's going to be 3x squared times 1, which is just simply 3x squared. Pretty straightforward. Now, on the other hand, We do the same thing with y. The derivative of y to the third in terms of x. So I differentiate that. So it's going to be 3y to the second times the derivative of y in terms of x. So notice up here it was dx over dx because the derivative of x to the third in terms of x. This here is the derivative of y to the third, or derivative of y in terms of x. So this one doesn't go away, it stays the same. It's just simply 3y to the second dy over dx. Now, let's go just a little bit more into it. Okay, the following, d dx, derivative in terms of x plus 3y. So let's do each term one at a time. The derivative of x is just 1 times derivative of x in terms of x plus, and then 3, the derivative of y is just simply going to be 1 times the derivative of y in terms of x. So this goes away, and we're just left with 1. 1 plus 3 dy over dx. All right. So you're seeing how the derivative of x in terms of x is just simply 1 because they cancel out. But the derivative of y in terms of x does not cancel. It just simply goes away. Now remember, we can rewrite this as 1 plus 3 y prime. Because remember, dy over dx is y prime. All right. Now, let's do this next one here. X, y squared. Here we're going to have to use product rule. So since we're going to use product rule, we'll do the derivative. And I'm going to write this out the long way, times y squared plus x times the derivative of y to the second in terms of x. All right. I hope this doesn't confuse you. Basically, I'm taking the derivative of the first times the second plus the derivative of the second times the first. That's all I'm doing. All right. So derivative of x is just simply 1. So it's dx over dx times y to the second. We'll simplify that in a moment. Plus x times the derivative of y to the second is going to be 2y times dy over dx. And then that's just simply going to give us y squared plus x plus 2xy dy over dx. That's what we end up with. That is an example of implicit differentiation. So basically we have multiple different terms. All right. Now, if you recall, the value of taking a derivative is it allows us to find the instantaneous rate of change. That's what derivatives is all about. The value of a derivative is the instantaneous rate of change at any given moment. That's what the derivative is all about, is determining that instantaneous rate of change. Remember, in algebra, you learned to determine the rate of change from between 2 points. Here in calculus, with derivatives, you determine that rate of change at exactly 1 point or at one instant. And this is represented by dy over dx. And we want to find dy dx for implicitly written equations. So, in order to do that, differentiate both sides of the equation with respect to x, collect all the terms involving dy over dx on the left side of the equation, and all of the others on the right. And then factor dy, dl on the left side, and then solve for dy by dividing. Okay, that may not make a whole lot of sense at the moment, but we're going to do one of those right now. Okay, so I'm going to differentiate this whole thing. So the derivative in terms of x of this whole expression is going to be y to the third plus y to the second minus 5y minus x squared equals -4. All All right, when I do that, it's going to look like this. The derivative of y to the third is 3y to the second dy over dx, plus the derivative of y to the second is 2y dy over dx, minus derivative of 5y is just simply 5 dy over dx, and then minus 2x dx over dx. Because remember, this is in terms of x in terms of x. Well, the derivative of negative 4, remember, it's a constant, is 0. So I have all of those. Then the next thing I want to do is remember that this becomes 1, so I'm just going to simply move this term over there, so it's going to be equals 2x. But all these have dy dx. So I'm going to factor out dy over dx times 3y to the second plus 2y minus 5, and that's all times dy over dx. Well, I'm still trying to get dy over dx by itself, so I'm going to factor out dy over dx, and I'm going to divide both sides by 3y to the second plus 2y minus 5. And this, you are going to have to take it to the very end, because you are looking for the value of dy over dx. All right. Now, I was hoping to get this next part done before the end, but we'll see how it goes. Okay. The slope of the line tangent to the curve y equals, or y squared plus xy plus 1 times 3 equals 0 at the given point. This is actually from an AP exam. So I'm going to do this on the second part, or part 2 of this video, because of time.